Okay, go ahead.
Hello, I'm Angela Martini, and I'm a current electrical engineering undergrad student at the University of Minnesota Duluth. I hold an AAS in electric utility technology at Fond du Lac Tribal and Community College. And from there, I've had some great NASA experiences. Actually, Carl Sack, who we just were speaking to from the last presentation, was responsible for most of that. And since 2020, I've been working with the Minnesota Space Grant with this focus on respiration monitoring and e-textiles. This time around, I'm here to talk about the exploration of piezoelectric energy harvesting. Using PVDF as a power source and respiration monitoring e-textiles. So today I'll be covering wearable vital sign monitoring garments and aerospace applications, and then moving into piezoelectric energy harvesting, circuit design, and finally data transmission and analysis of the data found from breathing rate measurements. Wearable vital sign monitoring. Wearable vital sign monitoring is becoming increasingly important in e-textiles. The common types include heart rate, blood pressure, respiratory rate, and oxygen saturation levels. The benefits of vital monitoring include real-time data on a person's health, detecting health problems early on, and leading to better outcomes and treatment. The role of e-textiles and vital sign monitoring would include embedded sensors and other electronic devices in clothing to be minimally invasive way to monitor a person's vital signs. Oops. This is from our previous publication. Last year we presented at the DMD. Okay, so it was entitled Concept of Exploration, Respiratory Monitoring Garment Using Digital Zero Crossing. So measuring respiratory rate is crucial for monitoring human health, but it's often neglected due to difficulties in accurate measurement. To combat this, a respiratory rate monitoring garment was developed that measures breathing rate in real time in an unobtrusive manner. The garment uses a stitch sensor that wraps around the patient's chest and operates based on the relationship between resistance and resistance. Digital zero crossing is used for improved accuracy and lower computational power. Performance of the garment is the real. Sorry, that's kind
That's good. Absolutely.
of. Is it too close?
Oh, it's my mistake. Don't worry about it.
Okay. Okay, where was I now? Okay. The performance of this garment indicates the real-time respiratory rate monitoring is possible, increasing the potential for improved patient health. And this is aerospace applications and vital sign monitoring. Vital sign monitoring is extremely important in aerospace missions or commercial airline flights. In these environments, individuals may experience a range of physiological changes due to factors such as altitude, gravitational forces, exposure to radiation, and devices used include wearable sensors, portable monitors, and other sophisticated medical equipment. In aerospace medicine, vital sign monitoring is critical due to the health and safety of individuals who work and have to travel through aerospace environments to access overall health and make decisions about medical treatment, evacuation, and emergencies. Here's some more pictures. Sorry, I put them in there. Abby was like, yeah, just put yourself in there. But that's one of my kids at one of our path experiences. Sorry if that's inappropriate for the setting. I hope you guys are okay with that. Okay. So piezoelectric energy harvesting. I can make more comfortable. Better. Thank you guys. All right. So this is the current submission. It's not published yet, but it's a theoretical piezoelectric energy generation from thoracic expansion during respiration for smart wearables. Yeah, just close out the tongue, right? So the structure of PVDF, I've been studying this for a year and I still can't pronounce it. Polyvinylidene fluoride. Okay, and it's a type of polymer material that can generate electricity when subjected to mechanical stretch such as bending or twisting. Here's how PDF works. The structure is a crystalline polymer that has a unique molecular structure that allows it to generate an electric charge when it is mechanically deformed. The structure of PVDF is such that it has polarized molecules, meaning that some of the electrons are pulled toward one side of the molecule, creating positive charge, while the other side is pulled to become negatively charged. Mechanical stress. When mechanical stress is applied to the PVDF, it causes the molecules in the polymer to shift and create electric charge. When bent or twisted, it causes positive and negative charges in the polymer to separate, creating an electric field and generating electric charge. The electric charge generated by the PVDF material can be collected and stored using conductive materials such as metal electrodes. These electrodes are typically placed on each side of the PVDF material and then forwarded to the electrical circuit to power devices and store energy for later use. So applications of PVDF include a range of potential, including wearable electronics, sensors, and energy harvesting devices. For example, PVDF materials can be incorporated into clothing or generate energy from body movements or used in sensors to detect mechanical stress or pressure, and in this case, respiration. Overall, PVDF generation is a promising technology and offers a renewable and sustainable way to generate electricity from mechanical stress. For further research and development, it has great potential to revolutionize the way we generate and store energy. I had a video, but it won't work. It was really neat. But thank you. Okay. Circuit design. This is what I came up with. So PVDF, it comes in little strips. I did have some that is back there, but it's like this, and when you move it, it generates electricity. So my theory is if we connect 3 rows of PVDF, because in series connection, we add the voltage. And so each one of these will, okay, so they generate about 330 millivolts each for sure. So that would sum up the voltage for each one. So that'd be, it's about a volt, I guess. And then we connect them in parallel because we don't get any current. And so the parallel connection will amplify the current some. And that's my reason for that. But I forgot to mention that PVDF is an AC power source. So it's going to have to go to the Schottky diode bridge rectifier, which is what will transfer it to DC voltage. So it can be used in this next part, but I'm not getting ahead of myself. Schottky diodes were chosen for their low voltage drop. And an ultra low boost converter to amplify a small VN. We'll get to that. So, and then it's going to go to a LoRa transceiver to transmit that data to an Arduino BT Bluetooth for analysis. Power in PVDF and bridge rectifier, AC to DC. With the series parallel array of PVDF piezoelectric sensors pressed and or strained, it will generate AC voltage. The Schottky diode bridge rectifier will convert the AC voltage into DC voltage that can be used to power a load and charge a storage capacitor. The rectifier will also ensure the polarity of the output voltage is always the same, regardless of polarity of input voltage. This technique, I believe, is pretty similar to what they do with solar arrays. It's kind of neat. It reminds me a lot of that compared to, but I don't think I need to go into that too much. So I'm expecting an approximate voltage drop of only about 0.4 to 0.8 volts, which is really good. Usually each Schottky diode or regular diode would be that a piece, maybe more, 0.6. It's a lot, kind of. So it wouldn't be very practical. So voltage application, this is the best part, my favorite part. It's a BQ25504 ultra low power boost converter. It's capable of amplifying voltage of about 5 times, although in this graph I did it at about 3.5 times each because it's about that RMS voltage. So I thought that that's generally a good line. So the orange shows how much I would get from PVDF alone by number of sensors on the bottom. So say One sensor is at about 0.33 volts, two would be that. That's what I could expect from this ultra low boost converter, which can make a lot more usable energy. And the blue line shows the BQ25504. So this boost converter has a BN minimum of only 330 millivolts, and then it can push out about 5.5 volts, which is very interesting. And it has, sorry, I'm getting lost and not sticking to it. Minimum input current of only 330 nanoamps, which is tiny and great. That's awesome. And a maximum output of 250 microamps. And that allows for very low power consumption, making it a most excellent choice in using energy harvesting and other low power applications, and is 80 to 90% efficient. Data transmission and analysis. So the BQ25504 power evaluation module can be used to power the LoRa transceiver and then connected to Arduino BT for data processing and communication. The LoRa transceiver connected to the Arduino BT can then begin processing and transmitting data. The BQ25504 will ensure the devices are efficiently powered and with minimal power consumption, making it ideal for use in energy harvesting and low power communications. The LoRa is a wireless communication technology providing long range, low power communications between devices. LoRa transceiver is a device that can be used to both transmit and receive data during using this technology. Overall, LoRa transceivers offer an attractive combination of long-range communication, low power consumption, and flexibility for a variety of applications. The Arduino BT was chosen for several features that make it ideal for wireless communication and IoT applications. These include the Bluetooth connectivity at Mega controller, USB interface, I/O pins, compatibility with Arduino IDE, which is pretty simple, and overall the BT is a versatile and convenient board for wireless communications and IoT applications, and can be used for a wide range of projects. Summary. Okay, so I'm still in development stage. I don't really have results. I haven't gotten all the parts I needed, so I don't actually have too much to show, but that's my plan so far. But after all my research, it does seem pretty feasible that TPP can act as a standalone power source, and the Schottky diodes can help with AC/DC power. That BQ25504 with excellent efficiency harvest, allowing the LoRa 890, 896 transceiver module will allow great transmission of data. And the Arduino BT keeps it simple and the power consumption low. I think it's possible. Even though I've been told so many times it's not, so I'll just say that right now. But I'm keeping going. So here's some thank yous. This one was Space Grant, U of M, D, Fire Lab, that's my lab, NASA, all my experiences, Fond du Lac Tribal and Community College, everyone there, Carl, my mentor, Dr. Abigail Clark Sather, Sam Carlson, Sandra, Wowers Sish, Don Home, Crystal Compton, Cody Lundquist, Dave Anderson, sorry, I could stop, Paulo, Destiny, Brenda, and my daughters. Yeah, you're there too. Oh, thank you. And okay, so Jerry Woodfeller is a guy from my Johnson Space Center experience. I got to actually meet him, as you can see. He was actually worked on the team with Apollo 13, and he did all this. He's a great. He was a great guy. I thought it was good. I get choked up. I'm not a good at it, but yeah, it's a good experience. Interesting. Anyways, yeah, that's pretty much it. If you made it this far, thank you for listening.
Sense for how long it might take for this
This
product to
time
be.
next year it'll be done for sure, and
Next
I'll
year?
have a lot more, and be a lot more confident with it, that's for sure. I hope to have a model built, at least the power source. It might not be in a shirt yet, but we have to have a paper done by May, so I'll keep you posted. Yes,
What is your expected lifespan of a garment that has a PVD coil throughout it?
That is a great question, and honestly, okay, so with our previous work, I have found that stitch sensor, it was a conductive thread that we use in the resistance versus displacement measurements. And yes, laundering is a huge concern, but that stuff came back okay. I'm thinking I'm gonna have to do some detachable devices. Obviously, it's gonna have to attach because of the LoRa, but I'm sure by then, I don't have experience. Sorry. Yeah, I'm sorry. I'll have to get back to you on that. Yeah, I haven't gotten that far. I'm sorry.
No, you should be sorry. I'm supposed to say, it'll last forever.
Yeah, I should have said that.
You'll be very impressed.
Any other questions? Yes.
Since it is like a web of garments.
Yeah,
How are
yes.
like body fluid, like sweat and oil. You can do that.
Yes, I'm worried about fabric. Sorry, I've interrupted you. What was the
Yeah.
last-
How would you avoid? Or do you have a solution?
I do not have a solution yet, no. But yes, it is a concern, but solution not yet. That's true. No, I'm sorry.
Think about laundering and like washing it, like how that goes as well, but.
Well, the other shirt, the conductive thread did launder well. I don't know how many times it will take, but I did wash it a couple times and it still worked. So, but that was a completely different setup and I'm totally dropping everything from before. I haven't got there, so I'm completely starting over on my own and figuring it out. So yeah, next year I'll know. I'll have some answers for you. You guys are here. Any other questions?
For the garment itself, are you looking at anything with like anti-static properties, or is there any issue with static?
That is a concern of mine that I have not gone to, well, at work, so I work at a place called JP Circuits, and we have this one material that we ground everything, and that's might be an option. I forget what the actual material is called. But we have to ground it, like when we work with MOSFETs and stuff. So I didn't even think about that until you asked, but I'm like, maybe that would work. Yeah, I'll probably have to ground it somehow with some sort of material that. There's a lot of stuff. Thank you for bringing that up. And I'm probably open to any other suggestions because I'm kind of glad I came here first before I started really building. Does anybody else have any other input, ideas? Yeah.
What are you doing to get rid of the excess energy that's being created from this?
That's a good question. I also need to find out like how much is actually necessary. I think with what I had shown here, I'll only need 6, but I showed 9 in the thing, but I'm probably gonna have backup flexible super capacitors. And I didn't include them in here because I haven't decided which ones I actually want to use yet. But I'm gonna have probably an array similar to that, but super capacitors.
And that's taking into account the transmission necessary to send the data somewhere?
Yes, well, okay. I'm not exactly sure how I'm gonna connect them yet, but it will be considered. That's pretty much the only reason why I left it out, but I have a whole bunch of information on it, but can't give a clear answer on that yet. Just not there yet, to be completely honest. Any other questions? Oh, I have a chat.
Why don't you see what's on the chat, but then we'll need to go on to the next
Okay.
speaker.
Oh,
You.
well, that was just Carl saying, oh, shucks.
Okay, thank our speaker again.
Okay,